Hello, this is Spencer Sheen coming to you with another R tutorial video. The topic today is actually coming by request of my channel subscribers, which is weird to say because this is only my fourth video, but I already have some subscribers who are engaging with me and asking me questions. So this video is going to be addressing a theme of questions that I've received. And so let me start by saying this image here on my screen is population density along the Seine River in France. This was one of my last videos that I created and I shared on my YouTube channel. And this data represents population density data. And the questions I've gotten from folks are how can they create similar graphics to this using different data? So how can you use different data and put it in a spatial context and visualize it in 3 dimensions such as this? So that's what I'm going to cover here today. So this is the last we'll see of this graphic, but I am going to keep us in France for this tutorial. Now, I've already created a repository on GitHub called YouTube Tutorials, and going forward, I think I'm going to try to keep my code in this repository for these YouTube videos. But this is the first one here, so this is a blank slate. I've created an R project here that I'll be working out of that's connected to the remote repository, so we're all set there. So the example that I'm going to cover to illustrate how you can use your own data to create a graphic like that is to download location data of French wineries, and let's create a similar ray shader graphic that illustrates the locations of French wineries. And through that process, we're going to cover how you can do spatial joins, how you can join point data with polygon data, and that's really the key for what we're doing here. So let's go ahead and get started. Now let's see, another question I've gotten a lot is, in my previous examples, I've used the Tigris package in R to download state polygons, the state boundary geometries. Apparently that package is only available to people residing in the United States. So I've received questions about how folks can go ahead and download similar data when they aren't in the United States. And one listener has had commented on one of my videos that there's a way to do it with the raster package. So I'm going to download the French data first using this package. So let's go ahead and get started. The function name in the raster package. So I've loaded the raster package. This function getData has a few capabilities. But if you look at the help page, you can see that there are a few different options for the arguments. So the name argument, for instance, you could use GATM, you could use the GATM data, which is what we're going to do. Or you could use countries, or honestly, I don't know what all of these are, world climate. So there are a few different options. But we can use the GATM data. I've never heard that said out loud, so I have no idea if that's how people actually say it, GADM. So we'll use the GATM.
We're going to say the country is France.
Let's see if I'm doing this right. Oh, they have an example of France right here in the help. So yes. So the country should be a 3-letter code for the country. And then the level is the administrative level of the country. So let's start out, just for to illustrate, let's just start out with 0. And as always, I want to make this I always prefer to work with SF data because that is just, if you're used to the tidyverse and working with data frames, it just works. It's much more intuitive. So I've converted the data we downloaded here to SF, and now I'm going to load the tidyverse too because I think we'll use a lot of those packages. GGPLOT plus GeomSF. So now I'm just going to plot what this looks like, just to make sure. This is always a good check if you have spatial data to go ahead and make a quick plot of it and see what you're working with. And there we go. All right, so this is the full country of France, but it's only the country. It's the administrative boundaries of the entire country. And that's not exactly what we want. My aim is to download the location data for wineries within France, and then I want to group those wineries by another level of administrative district. So that I can then distinguish between the different areas. So to do that, let's call this France level 2. And I'm going to do the same thing I did here, but I'm going to say level 2. And once again, let's go ahead and plot this. Just to see the difference of what we're working with. All right. So there you go. Now we can see I believe these are departments of France. And great. So now you can kind of get a sense of when we go ahead and plot our wineries, they'll be arrayed around, for instance, like this, and we'll be able to group them by these different departments. And then we can use GGPLOT to illustrate the concentration of wineries. And we can also throw it in Ray Shader and simulate some 3D graphics and cast some shadows, because that's always fun. Okay, so to download the winery data, I am going to use the OSM data package. Now, OSM data, if you're not familiar, it connects to the OpenStreetMap API. So OSM, that's OpenStreetMap. And contrary to the name, there is a ton of data that they make available. It's not just roads and streets and highways. It's it's a lot. And so we want to download wineries. And I will show you quickly how you can go about searching the names of things within the OpenStreetMap database so that you know how to query it. So I'm going to look up OSM features, because these are the names of map features within their database. And you have to be able to call the feature by its key and by its value. So I guess I can go ahead and show you the basic structure of how we're going to set this up. I'll get to this in a minute, but the way the query works is you add OSM feature. So you add something with this function to the query. So you're going to be requesting a specific key equals something we need to find out, and a feature. So this key, or no, I'm sorry, value. This is a key value pair that we need to pass to the API to get the data that we want. So that's what we're looking for here. And we're looking for wineries. And so this whole page is broken down by the type of data that it is. So for instance, aerial ways, amenities, these would be like places. You have barriers, administrative boundaries are also available. Highways, you have all these highways. So you can see there's a lot of different categories, and within each category, there's a lot of key value pairs. So the fastest way to navigate this page is just to search for what you want, honestly. So I'm going to search for winery, and there we go. So we can see here, oh my goodness, there are so many crafts. So we have key is the left column and value is the column right next to it. And so craft is our key and winery is our value. Okay, now to hop back up here, this function is the spatial boundaries for where you want OpenStreetMap to query this data. So here we're telling it what data we want. We're saying we want wineries, but first we have to tell it where we're looking. And you do that by passing in a bounding box. So let's look at the OPQ help page. And you can see the first variable here is the B box. That's the bounding box. Now, this function does allow you to enter something like Bordeaux, France. But before I started this recording, I was testing this out and I tried passing in just France and it wasn't working for me. We can give it a shot, but I don't have high hopes. The final thing, before I pass this query, I'm going to set it up to translate as SF data again. Okay, so let's try that. Let's see what we get. That was too fast, I can tell you right now. So we're looking for winery locations. So you might intuitively guess that we're interested in point data. So now if we look at wineries, OSM points, this is the data that was returned by this query. We see we have 0 rows. So 0 rows were returned. Now, I think I honestly don't know why passing in France doesn't work. Because if you pass in Bordeaux, for instance, I had better luck with that. Yeah, see, better luck with Bordeaux. We get a collection with 82 features. That means 82 different observations or 82 wineries. So maybe it's just the large size. It's not passing it in well by just the name. In any case, a workaround here is to create our own defined bounding box. So stbbox will create a bounding box around a spatial item. For instance, here, I'll go ahead and save this. Okay, so this is a function that's creating a bounding box around France, this France polygon that we created up here. Now let's visualize this so you can understand what's happening. So first we'll plot the France bounding box, but let's add another layer where the data is just France. That didn't work. Oh. Okay, so the France BB object here, you can see returns in the corners of the box. So the minimum X value, the minimum Y value, the maximum X value, and the maximum Y value. With these 4 values, we can create the 4 corners of this box. So that's what STBbox does for us. And here you can see I plotted the box. So this is the box, the bounding box. And then France is plotted in red. So you can see the bounding box is just the maximum extent. It creates a rectangle that is the maximum extent of the polygon. Okay, so that's what we want to pass to the OPQ function here. All right, so let's try that. All right, that looks like an error, but let's... Yeah, that's the same. All right, remove wineries so we don't get confused with that Bordeaux one I did. Sometimes when you're working with the OpenStreetMap data, this happens. You get errors on the call, the API call. So you can just try again. In my experience, the errors come more frequently when you're working with larger data sets. So here, querying a bounding box for all of France is a kind of large data set. So I'm not terribly surprised that that just happened. Ha, there we go. So now I'm going to take out the point data from this, the OSM points, because I don't need the lines, I don't need the polygons or the, feel free to explore these if you want, but I just want the points. Okay, so now, once again, hang on, I'll take that out. Let's call it wine points. I hate not having the plural be intuitive. Okay, let's again plot France. But this time, let's add the layer of these points. Data equals wine points. All right. Now we're cooking with gas. So you can tell that some of these points, each point represents a winery, and not all of these points are actually located in France. You can see they're outside the borders of France, but they're inside the bounds of the bounding box. So these represents points, again, that are within the bounding box. And the bounding box is actually larger than France itself. I assume these wineries are in England, and they are not in the English Channel. but we'll just take that on face value. I have not been commenting my code at all, so let's add a little bit of comments. Okay, download. Oops, that's not right. All right. So now we have the two pieces of data that we need. We have the French administrative levels. These are the polygons that we want to group our winery locations by. So we want to say for each department in France, this is how many wineries are located in it, within its boundaries. And we have our winery locations. So now we can do that. So we need to join winery locations with departments. And I'm not feeling very creative right now, so I'm just going to call it joined. And there is a fun function called stjoin that will allow us to do this. And let's look at the help page. So I'm going to assume that you have at least a passing understanding of joins in data manipulation terms. So joining tables together. This by default will do a left join, and a left join, as a reminder, will keep all values in the x on the left side of the argument of the function. So this x value, it'll keep all the rows in x, and it will only join the y values that intersect with x. But what we want to do is we want to do an inner join, actually, so that only the values of x, which will be our point data, we only want to return those values that intersect with the French departments, because we don't care about these wineries that are outside of France. So our left side of the join is wine points. It's our wineries. And I just remembered something. Let's take a look at wine points. Yeah, so the data returned by OpenStreetMap is a lot. So these are all the columns that are present in this data frame. We don't need all of these columns at all. In fact, all we need is the geometry column. So I'm going to just select geometry so we are less cluttered. Okay, so we're joining the wine points with France level 2. And then left equals false. And again, left equals false. If true, return a left join, otherwise an inner join. So if it's false, it's going to return an inner join, which again means it's only going to return those values on the left side that are present in both. So those values, those wineries that intersect with any French departments. And that was pretty fast. So now we have our joined object. And if you compare wine points, this is all of the wineries returned by the OpenStreetMap data by the API. You can see we have 23,000, but when we do the inner join with French departments, it cuts it down over half, so down to 10,000. And remember, I just selected the geometry column, so wine points only includes the geometry. So what's happened here is it has joined the point with all of the data from France level 2 from this data frame. All of the data except for the geometry for the department. You'll see in the France level 2 data frame we have the geometry, the multi-polygon, but once we've joined, because the left side of the argument was our point data, the winery locations that are just points on a map instead of a polygon boundary, that's what's returned. That's what's maintained in this. So what we need to do now is summarize this join data by the department. And if we look here again, the department is designated by name 2. Or I guess the ID is GID2, so we can do that. So joined GID2, and then count. Let's see what that does. Now, because this is an SF object, it maintains the geometry for us. Even though I didn't add it as a group by, it adds it. And you can see we have our GID2 here, this ID for the departments. And now we have this column in, which is showing how many points were located within that, that department. And now our geometry is actually a multi-point. So it's showing all of the points within that department in a single row. So let's save this to an object SUMJoined. And now now we need to join it back with our departments. And so there, depending on the final visualization you want to make, there's a few different ways you could do this. You could maintain this column with all of the points, but at this point, we don't need the point spatial aspects anymore. We just need these two columns. So I'm actually going to say SUMJoined as Tibble Okay, so if I say as Tibble, that's changing it from the SF object. And remember that when it's an SF object, this geometry column is always maintained. By definition, this column will always be maintained. So to drop this column, we need to convert it from an SF to a regular data frame or a Tibble in tidyverse syntax. And then I'm selecting away that column. So now I have the ID with the counts and no geometry. So now I want to do a normal left join with our France level 2. Is that going to work? Yes, that works. call it level 2 counts. Okay, so then level 2. So now you can see in this data, we have our geometry, but we also have a variable that we can map to the coloring. So we can create a heat map. Level 2 counts. And let's say the fill is mapped to N, and then there we go. So this is showing us a map of France, all the departments in France, and the coloring is tied to the count of wineries within each department. So you can see these departments are well above the others. Okay, so now we have the data in a format that we can use to plot it in Ray Shader if we wanted. Similar to the population density maps that I've used, those start out with the contour population data, which is in data frame format. And so if you follow my code for those or the tutorials, you'll see that we take an SF data frame and then we convert it to a raster and then to a matrix. And so if you just swap out this object for the contour data that we start with, then you could follow those steps and you'll be able to plot it pretty easily. I'm not going to get into that here. Instead, I'm going to show you a couple other things. So for this data, we have downloaded the winery data from OpenStreetMap here. And the data is returned to us in a spatial format. That was a nice feature of the OSM data package and these functions here, that it returns it to us in easy format, so we can go ahead and plot it directly. But what if we have data that is not already in SF format? What if we have a data frame, or say we have an Excel file, a spreadsheet, and there are two columns, there's a latitude and a longitude column. How do we take that and convert it to our spatial format so that we can do all these same steps here? To show you this, I'm going to first convert our wineries data out of SF format. So that I can show you what it's like if the data is not in that format. So wineries. Wine points. We'll call it wine chords because we're getting the coordinates for the winery. And you can see, so this returns, well, as a reminder, if we look at wine points, we have limited it to the geometry column, and then if we do ST coordinates on it, then it returns X and Y coordinates for each point. So you can see there's the same number of rows, so 20,064, as there are in wine points, 20,064, and that's what we should expect. Okay. So we now have wine chords is exactly what you might have in an Excel spreadsheet where you have data that is in your latitude and longitude coordinates along with other data. So now let's convert it to SF format so that we can easily plot it. And luckily for us, this is not very hard to do given the SF package. Let's see. ST as SF chords equals. I'm gonna try to get this right before I explain it because I always get a little bit confused. Okay. I thought it was ST as SF. So two things just happened. If you notice, when I originally created wine chords, I just did this bit of code, ST coordinates on wine points. And you can see that did not return a data frame. That did not return a data frame. What is this, a matrix, an array? So essentially a vector. Yeah, it's an array. And so to convert it back to ST as SF, we want it to be as a data frame. And also, if you're importing a spreadsheet or something like that, you probably have it as a data frame already. So an easy way to convert from that array to the data frame is just to use as Tibble again. Okay, so once we've done that, then ST as SF can take a data frame where you have the coordinates present, and you just need to specify what the coordinates are there. So I've done that here. Chords is XY. And then we also need to pass it the CRS. And this is the basic CRS. These coordinates, I believe, but we could also check STCRS. Yeah, 4326. Whenever you have these coordinates of this standard, like 0 to 90 or 0 to 180, that's the basic CRS is EPSG 4326. And so whenever you're converting, you can pass just that EPSG number to CRS just to specify what the CRS is, the coordinate reference system. So now we have our data back in SF format. And just to show you, we can go ahead and plot again. And there we have it. We have all our wineries showing up again. Okay, the last thing I want to show you, well, first, just to tie a bow on this. So now you could take this data frame that's now in SF format and replace it starting here and just continue. So you do your join with that data frame and the polygons, and you would just go on as normal from this point. Okay, next I am going to cover how we can create our own polygons to group this data instead of using these administrative boundaries. Depending on the granularity of your data or the ultimate visualization you want to make, it might not make sense to be grouping by these geographic boundaries, you might want to create something a little more granular. For instance, you might want to create a grid of geometries that covers this area and group by that grid. And if you're familiar with the population density maps that I've done, that's what those show. It's a grid of hexagons, and the population is grouped by those hexagons. So let's make a grid of hexagons and group the winery data in France by those hexagons. All right, so we're going to group by a hex grid. Now the first thing to do is use stMakeGrid from the SF package. And since I want it to be limited to France, I'm going to make the grid over France. And then, so if we look at the help, we see that there are these arguments that we can specify. And I just set square to false, because if false, it makes a hexagon grid. If true, it makes a square grid. There are benefits to hexagon grids because it creates an even spacing in all directions. So I prefer hexagon grids. Let's just try that. Let's see what that looks like. Okay. So we have our hexagon grid, but it doesn't look great. There are two things. One, these hexagons are probably a little too big for what we want. And two, they are squashed. So they're longer than they are, they're taller than they are wide, and I don't really want that. But you get these poor transformations when you're working with this 4326 CRS, or it might not be that one, but the issue is probably going to be that we're working with a coordinate reference system that isn't great. So let's actually examine what we have in France. So it's coming through as this, coming through as meters plus so that's an issue. So this data is in the 9122 CRS, but GGPLOT is not recognizing that CRS. So I think that must be what's happening. So let's just convert it to a different one. And so whenever I'm trying to convert, a simple thing to do is to just Google the area that you're looking for and EPSG. There might be a better way to do this. I'm sure there is, but this sometimes works for a quick solution. It's like 2154. Let's try that. Okay, let's ST transform France. CRS equals 2154. st make grid. Square equals false. All right, there we go. Now our hexagons are looking a little better because we've converted it to a CRS that works a little better. I am not a GIS professional. This is more a hobby of mine, so describing this is a little out of my depth at this point. So I'm not going to get into it. But suffice it to say, we now have a hexagon grid that looks pretty good. Now, the other thing that I mentioned is that these grids are too large. So let's look at the help and see if we can determine. So the cell size of the boxes is actually determined dynamically, it looks like. So I was hoping that it was just a number that I could then tease out, but let's just start with 10 kilometers. All right, that is a much more granular grid. Maybe 20. Well, we'll stick with 10. We'll see how this goes. Okay, and so the other thing you can do is hex grid. Let's see if I remember how to do this. Oh yeah. So I'm gonna need this to be in. Okay. I need it to be in the CRS that matches the data. And so I believe this is how we can set this up so that the hex grid is only showing those hexagons that overlap with France. All right, this is taking longer than I want it to. Let's make the hex grid bigger. Because I just want to make sure this is working. Okay, yes, that is how we want to do that. All right, so I'm going to keep it at 50,000, the size of the hexagons at 50,000 here. This is a little bigger than I would probably want it if I was actually making something. So you can go ahead and change this size if you want, but just know that that will take a little longer for some of these operations. So, sorry, I got something in my throat. France hex, let's call it that, and then hex grid. You should probably save this to its own object so you have it and you don't, so you just have it. France hex. All right, there we go. So now we've created our own geometries here to work with, and that takes us to this point. So now we need to do the join again. We need to summarize by the geometries, and then we need to join those summaries with the counts. So let's just go ahead and copy this. Actually, yeah. With hexes. Okay, so let's call this joined hex. We're still working with the wine points, but instead of the France level 2, we're using the France hex. Okay. France hex SF. That's apparently not an SF package, or STSF. Let's see if that works. Okay. So again, SF, you can just say STSF and convert this to an SF object. And we need it to be an SF object for the join. Shoot. Okay. So now we need our wine points to be the same CRS. So let's say st transform wine points CRS equals st CRS France hex SF. Oh yeah, hex. Okay. Okay, so I converted the France hex object to an SF object using STSF because we need it to be an SF object for the join. And then I needed the wine points object to be the same CRS as the hexagon object. And remember, we converted the CRS of the hexagon object so that it would plot better, so that the geometric operations to create the hexagons would work better and they would be evenly spaced. So we converted the CRS. So that means now we need to make the wine points the same CRS. So we've done that here. And then after those steps, we were ready to do the joined. And so now we have the joined hex. All right. But now we need to group by something, and I have taken away all of the arguments. So let's see if we can do that. Sum joined. Oops, and I just overrode that. Oh well. Okay, so I need so when I did the st make grid, that did not give us any other variables. It just, in the end, it just created this fr hex. So I need to create a dummy variable that will be joined with the data. So let's just call it dummy equals row number, or let's call it index. So now this is essentially creating an ID for each hexagon here. And so now if I do this again, do it again, sum joined hex, group by end. Oh, joined hex. Okay, God. Okay. So now we have, what did I do? Oh, I did count. So now we have the data we were looking for, just like when we were working with departments. So now we have the data we were looking for, just like when we were working with departments. We have the ID of the geometry of the hexagon along with the count of wineries in that hexagon. So next up, I gotta remember to make these. This is where copying and pasting can be a little tricky. Less geohex, level 2 let's call that hex counts. Hex counts. This is less geo hex. This one should be, instead of France level 2, it should be France hex XF. All right, let's see. Hey, it worked. All right. So there we go. This is now showing us, this is a little bit more granular detail. Not too much more granular than the departments themselves, but oh well. Like I said, you can increase the granularity of this by making the hexagons smaller, but this is showing us what we want. We have the grouping of the wineries within the hexagons. And so we can see the distribution of wineries across France. We have a bit of a heat map here. So just so that we have a thumbnail to work with for this video, let's go ahead and make this look a little prettier. There we go. Okay. I'm going to call this video here. So we have shown how you can take your spatial data, any of your spatial data, and combine it by different geometries, group it by different geographic areas such as departments or states or counties. You could use this technique for all of those different kinds of areas. Or you could define your own area using these grids, a grid such as this, for instance, and group your data in that way and summarize it and plot it just as you would with normal ggplot. And then from there, you could take this data and pass it to a package like RayShader and create some really interesting 3D graphics with that. So I feel like this was a bit of a meandering video. I hope it's still helpful. But in any case, thanks for watching. If you haven't already, check out my other videos that show you how to create RayShader graphics and learn how you could take this data we covered here and make a cool 3D graphic with it. Thanks.